When you're reading about AI, have you ever come across terms like generative AI, LLM, LangChain, RAG? My name is Will. I'm a software engineer at Google, and I share knowledge around coding. In today's video, I will break down what is large language model and guide you through the life cycle of building an AI-powered application. By the end of this video, you will have a clear roadmap how to start your AI journey. Let's start. To begin with, let's get familiar with some concepts. AI, or artificial intelligence, refers to technology to enable computer to process, analyze, and learn from unstructured data to perform specific tasks. The unstructured data including data format like text, image, audio, and video. And for the tasks it can perform, including classification and prediction, etc. For example, you could use AI model as an image classifier. You feed it with an image, and the model will tell you the animal in the picture is a dog or not. AI is a huge topic. We cannot cover everything in one video, but knowing that AI is making machine more smarter, that'll be enough for today's video. Then, what about generative AI? Generative AI is a subset of AI that focuses on generating content. The contents can be in form like text, image, and even code. For example, with image generator, you can provide model saying, I want an image of a dog, and the model will generate an image based on your input. Large language model, or LLM, refers to a model for one type of generative AI. This generative AI focuses on the text generation. LLMs are the engine behind the tools like ChatGPT that helping them to generate human-like text. Here is a simple way to think about it. Generative AI generates all kinds of content like image, audio, etc. The text generation task is just one small subset of generative AI. On the other hand, LLM are the powerhouse for the generative AI that focused on the text generation task. In LLM, the prompt is the input you provided to the model, like what you type into ChatGPT. The completion is the model's output based on the prompt, like what ChatGPT responds to you. Most of popular AI models today are around text generation. These fall under generative AI category. The magic behind these models comes from something called transformer architecture. Before the transformer architecture, we used a different architecture called recurrent neural network, or RNNs. RNN predicts next word based on previous few words, but they always miss the broader context of sentence. The context missing can cause inaccurate output. That's where the transformer architecture changed the game. The transformer architecture is introduced by the paper called Attention is All You Need. Yes, that's the title of the paper. I love it. And the transformer architecture made a huge improvement on how models handle language tasks. The secret is self-attention mechanism. Self-attention mechanism allows model to understand how each word in a sentence related to every other word in the sentence, not just the previous few words. In this way, model can preserve all of the context of a sentence, and it solves the issue made by RNNs. In the original paper, the self-attention process are done many times in parallel. This process is called multi-head attention. This is a diagram of transformer architecture. In today's video, we only need to pay attention to high-level architecture of it. The detail of it, I will cover it in later videos. This is the simplified version of it. As you can see, there are two main components of it, the encoder and the decoder. The encoder processes the input sequence and create high-dimensional representation of it. The self-attention layer in encoder only processes the whole sentence of input. The encoder uses encoder's output along with other informations to generate the final output sequence. The loop over here means the previous output of decoder will be used as input for next token generation. The decoder has two types of attention. The first one is called self-attention. In these attention layers, decoder only looks at previous generated tokens with no other informations. And the other one is called encoder-decoder attention. Encoder-decoder attention take encoder's output and previous decoder's output as whole to send into the attention layer. I should point out that even though encoder and decoder comes together in original paper, but themselves can serve as the architecture for the model, what we call encoder-only model and decoder-only model. Even though encoder can only learn the high-dimensional representation of input, but based on this representation, we can train different models for specific tasks we want. For example, we can train a model for sentiment classification based on the encoder's output. This kind of model we call encoder-only model. BERT is a well-known encoder-only model. On the other hand, decoder-only models are widely used today because of the scaling law. The scaling law means as the model size grows, the capability of it will grow as well. GPT family and LLaMA models are famous decoder-only models. That's enough for the detail. Let's go back to the high-level view of generative AI project lifecycle. The model itself only takes input and generated output. It's like a chatbot, but the model can be used in many different ways to integrate into today's application so that it can serve better to the users. Here are the steps to build applications with generative AI integrated. The first step is define the project. We need to find the right problem we are solving and the right audience before we start any implementation. We also need to identify the usage of generative AI in our application. Do we want it to do the classification, or we just want it to do the translation for us? The second step is to train the model or find the pre-trained model online. Once we identify the usage of generative AI in our application, we can search online to see if there are any pre-trained model that can fit into this usage. In this step, we also need to take model's architecture into consideration. It depends on our usage. For example, we only want the pre-trained model to generate high-dimensional representation of input. We can use encoder-only models. On the other hand, if we wanted to do the text generation, we can consider the decoder-only model. If there is no existing pre-trained model, we should consider training from scratch. But pay attention, training from scratch, we need to consume a lot of computer power and a lot of data. That's why the suggested way to start this step is to find the pre-trained model online. I call the third step as model improvement. The pre-trained model can be capable for all of the tasks, but only in average level. If we want model into our application, we want model can do expert level in the task we want them to do. In these cases, we need to do some improvement to the model to make it fit into our application. There are many techniques we can use in this step: prompt engineering, full fine-tuning, and parameter efficient fine-tuning, or PEFT. In prompt engineering, we can formalize our prompts that we provided to the model to lead model to generate output we want. We can also provide examples in the prompt to let model learn something more specific, or we can continue train the model based on the data set specific for this task. This process is what we call full fine-tuning. In full fine-tuning, all of the parameters in the model are trainable and will be modified during the training process. I need to point out that, similar to training from scratch, full fine-tuning also need to consume a lot of compute power and data. Then it's naturally come to mind that can we only train small set of parameters instead of for all of it. This comes to the third way to fine-tune the model, what we call parameter efficient fine-tuning, or PEFT. In PEFT, there are many techniques we can use here. For example, we can froze most of the parameters of the model and only train a small set of it. That's we call the selective way to do that. Or we can transform in the parameters space to enable more efficient training process like LoRA. Don't worry, we will cover these techniques in later videos. The fourth step is what I call model enhancement. So far, we only have a standing alone model. It takes users' input as prompt and provide completion based on that. However, there are many challenges with it. For example, knowledge cutoff. You might notice that when we train the model, we need to provide dataset, but anything happens out of dataset will not be included. If you train the model in 2025, it will never know the things happening in 2026. We need to overcome these challenges. Instead of improve model itself, we should let model to interact with environment. I call this process model enhancement. There are many ways we can do to enhance the model. The first approach is reinforcement learning from human feedback. This involves connecting the model to the external environment. With this method, the model can first interact with surrounding environment. Second, collect feedback from human. Third, refine itself based on human feedback. The second approach is called Retrieval Augmented Generation, or RAG. Instead of let model interact with human, we provide model ability to connect it to database. So it can retrieve information from database for every prompt. We combine retrieved information along with user's input as the prompt to send to the model. Combining retrieved information with user's input as prompt sent into model, the model can generate more robust response. The third approach is called Programming Aided Language Model, or PAL. You might sometimes notice that model cannot do the calculation correctly. Instead of letting model do the calculation itself, we let model to generate Python code based on the task. And then we connect model with the Python interpreter, and we let Python interpreter to run the code to do the calculation for you. In previous examples, we made decision for the models. For example, we let model to retrieve information from database. We let model to write code for us. How about we let model to make decision for itself? So in this case, we want model to start reasoning. Based on the reasoning, the model find out it needs to generate code instead of doing the calculation by itself. Luckily, we already registered coding as a tool that the model can use. During the coding, the model find out one of the algorithms it doesn't know how to implement. So the model comes to the internet and search for the answer by itself, then back to finish the coding. This is the framework that's widely being used today called LangChain. The model enhancement part is very exciting area. We have unlimited imagination about it. Let's talk about it more after the model improvement video. The last step is called integrate with application. With above steps, we have a powerful generative AI that we can use. However, that's totally not enough for building an application. There are many components other than the model itself. For example, we need to build a data pipeline that collects user feedback or any usage data, so we can continually training model. Besides that, we also need to take care of application interface like website or mobile app. That's wrapped for today's video. We covered a lot today. The first, we covered some basic concept of AI, generative AI, and large language model. We covered a lot about transformer architecture, and then we go through the life cycle of a generative AI project. I hope this gave you a solid foundation to start your own AI journey. It might seem like a lot at first, but when you break it down, it's very exciting to see how these things come together. If you enjoyed the video, please like and subscribe so you don't miss future videos. I will dive deeper into model improvement, LangChain, and more other topics. Thanks for watching. I will catch you guys in next video.